G'day Year 9s, carrying on with frequency today. We're talking about relative frequency and probability, and experimental and theoretical probability, so we'll have a little bit of a chat about those. The number 2 here, which I've set for you, is this kid Rashid is rolling an ordinary dice. It's a 6-sided dice. He rolls it 12 times, and he rolls 6 3 times, so that the experimental probability is 1/4. In other words, what he's done there, he's gone, I got 3 out of the 12 times that I rolled the dice, I got a 6, so that's 1/4. And he says that the dice must be biased because you should be getting a 1/6 of the time, and we've got to explain why he's wrong. The reason he's wrong is he's only rolled the dice 12 times. We would say to him, roll more times. Now, if he rolls 1,000 times, for example, and finds that he's getting 1/4 of his rolls as a 6, then he might have a reason to think that the dice is biased. But in small numbers of trials, these kinds of results are quite likely and possible. It's over the long term that the theoretical probability is reached when you're doing an experiment. So the more rolls that you do, the more certain you are of the actual probability, the relative probability. Okay, now number 3, we're doing this one here. This girl's doing some favorite ice cream flavors, and we want to estimate the probability that the next person will like vanilla. So what we do is we add all of these numbers together to find out how many we've got. So I'm just going to quickly chuck that in my calculator. 64, 45, 52, 38, and 51. This is 250 people. Okay, so 250 people. What is the chance that the next one will like vanilla? Well, 64 of the 250 do, so if she just picks somebody, 64 250th, and perhaps we could simplify that down to 32 over 125. Okay, that's cool. Now, let's move on to the chocolate or strawberry. Now, chocolate or strawberry, you can see that you've got 45 here and 52 here. So altogether, that makes 97 out of 250 chances. So 97 over 250, can't simplify down, so we'll just leave that there. Number 3 is not raspberry. Okay, well, you know there's 250 results altogether. Raspberry is 38, so we could just go 250, take away 38. Now, 250 take away 38 gives me a 212. So I should have 212 over 250. And if we simplify that down, because we can, should be equal to 106 over 125. Okay, that's that. Now, B. Which flavour of ice cream should Jess order the most of? Obviously, vanilla. Not just because it's the best flavour, but because that's the one that's most popular. Okay, C. Can you tell from this table which flavour she should order least of? Explain your answer. Well, you could say probably raspberry, but you're not entirely sure. I'm going to say probably raspberry. But because you've got so few trials, there's only 250 people, and the difference between the chocolate and the raspberry is quite small, then it's not entirely clear. It's probably raspberry, but it could be chocolate. Okay, now let's move on. We've got this lady who suspects that the 6-sided dice is biased, and she rolls the dice 300 times and gets these results. How many times would we expect a score to occur if it was a fair dice? Well, you're going to go 300 divided by 6, and that should be 50 times for each. Okay. None of the and you look at this, none of the results equals 50, right? That's not 50, that's not 50, that's not 50, that isn't, that isn't, that isn't. Does that mean the dice is biased? Well, no, of course not. Just because you roll the dice 300 times doesn't mean that you're going to get exactly 51s, exactly 52s, exactly 53s. Right? It doesn't work that way. You're going to get approximately very close to 50. And again, like I said in an earlier question, the more trials that you have, the closer you're going to get to that expected probability. Okay, so C, do you think the dice is biased or fair? Okay, I think it's biased because of this result here and this result here. You can see that these ones are around about 50, but 23 is a lot lower than 50, and 77 is a lot higher than 50. So I would say it's biased, but do more trials to make sure. If we did 600 trials and this continued on, then you would know more with more certainty. Okay, the next one, we're doing this random experiment with drawing pins. Chucking them up in the air 50 times and seeing which way they land. Okay, now part A for 5A, we're trying to determine the experimental probability of the pin landing up. Well, we threw it 50 times, so the 50 times is our denominator. Out of 50 times, how many times did it land up? That's this one here, so it's 27. Okay, nice. Now, then we repeat the experiment, and perhaps, can I? No, I don't think I can. No, that's fine. B, we're repeating it 1,000 times, and now we've got to find the experimental probability of it landing up. Well, that's 42 over 1,000. Okay, which is equal to, let's simplify that down, 21 over 50. Okay, we've got to give our answer as a decimal. So 27 over 50 is 0.54. 4, sorry. And this one, 21 divided by 50 is 0.42. Okay. So, C. Out of the two probabilities, this one and this one, which is closest to theoretical probability and why? 0.42 is because we have done many more trials. Okay, that's the key idea. Number 6. A bag contains an unknown number of balls. The balls are coloured blue, red, and green. One ball is taken from a bag at random, and the colour is recorded, and then it's put back in. We do this 200 times, and the results are shown. Okay, these are very cool, these questions. If there are 50 balls, we've got to suggest how many there would be. Okay, so we did the trials 200 times. So 80 out of the 200 trials were blue. And so we're going to times that by the number of balls that we know are in the bag. Right? So that means that we expect about 20 blue balls. Now we're going to do the same for the red. 52 out of 200 times 50. And now this one is going to give us, hang on, is it 50? Yeah, it's 52 over 200. 52 divided by 200. And we're going to times that by 50. This gives us 13 red balls. And finally, the green, 68 out of 200 times 50. So 0.34 times 50 gives us 17 green balls. Now, you can do a quick addition here. 17, 20, 30, 50. Yeah, okay, good. So that would be my expectation. So what I've done there essentially is found the experimental probability of pulling out one of those balls and times that by the number of balls that I know are in the bag, and that should give me the number of that type of ball in the bag. If we get some time when we get back to school, I'll do a bit of an example of this so you can see how it works. Okay, well, that's all for the exercise. Take care, team. See you later.